So here's something you probably haven't thought about in a while. Numbers. Not anything complicated, just the basic idea of counting. 1, 2, 3. You learned it so young that you can't even remember learning it. It feels as natural as breathing, as automatic as blinking. But here's the thing. Counting is an invention. Somebody, somewhere, tens of thousands of years ago, had to figure it out. Had to look at a group of things, stones, sheep, days, whatever, and come up with a way to keep track of how many there were. And that moment, that first flicker of mathematical thinking in a human brain, might be one of the most important things that ever happened. More important than the wheel, more important than fire, maybe. Because once you can count, once you can represent quantity with symbols and manipulate those symbols according to rules, you've unlocked something enormous. You've opened a door that leads, eventually, to everything. To architecture and astronomy and navigation and engineering and computers and cryptography and quantum physics and the phone that might be sitting on your nightstand right now. All of it traces back to someone, a very long time ago, scratching marks into a bone and thinking, this mark means 1. This mark means another one. Together, they mean 2. And that's what we're going to talk about tonight. The entire history of mathematics, from those first scratches in bone, all the way to the deepest ideas that people are wrestling with right now, in the 21st century. We're going to take it slowly, because this is a story that deserves to be told slowly. It's not a straight line. It loops and doubles back and jumps across continents and centuries. It's full of people, real people, with rivalries and obsessions and heartbreaks and moments of staggering brilliance. Some of them are names you'll recognize. A lot of them are people you've never heard of who changed the world anyway. And if you drift off somewhere along the way, that's completely fine. The math will still be here. It's been here for a very long time. Let's start with the oldest mathematical object we've ever found. It's a bone. A baboon fibula, actually, discovered in the mountains of what is now Eswatini in southern Africa. It's called the Lubombo bone, and it's roughly 43,000 years old. Carved into its surface are 29 distinct notch marks, evenly spaced and deliberate. Now, nobody knows for certain what those notches represent. Some archaeologists think it's a tally stick, a simple counting device. Others have suggested it might be a lunar calendar, tracking the roughly 29.5-day cycle of the moon. Either way, it's evidence that someone, 43,000 years ago, was using marks to represent quantities. That's mathematics. Primitive, yes, but real. There's another famous artifact, even more suggestive. The Ishango bone, found near the headwaters of the Nile in what is now the Democratic Republic of the Congo, dating to about 20,000 years ago. This one has 3 columns of notch marks, grouped in patterns that have fascinated mathematicians for decades. One column contains groups of 11, 13, 17, and 19, all prime numbers. Another column seems to show a pattern of doubling. Now, it's dangerous to read too much into scratches on a bone from 20,000 years ago. The people who carved the Ishango bone left no written explanation. We're interpreting, and interpretation can be wishful. But at the very least, these bones tell us something profound, that the human impulse to count, to organize, to find patterns in quantity, is incredibly old. It predates civilization. It predates agriculture. It predates writing itself by tens of thousands of years. But counting is just the beginning. Counting tells you how many sheep you have. It doesn't tell you how to divide a field, or predict when the river will flood, or figure out how many bricks you need to build a wall of a certain height. For that, you need arithmetic. You need geometry. You need something more structured than tally marks. And the first civilizations to develop that kind of structured mathematics were the ones that needed it most. The the civilizations built around rivers. Think about ancient Mesopotamia, the land between the Tigris and the Euphrates, in modern-day Iraq. The Sumerians, and later the Babylonians, built one of the earliest complex civilizations on Earth, starting around 5,000 years ago. And they had problems that demanded mathematical solutions. Their economy ran on agriculture, and agriculture in a floodplain means irrigation, channels and levees and reservoirs, all of which require measurement and calculation. They had trade networks stretching hundreds of miles, which meant they needed accounting systems. They had taxes, which meant they needed ways to compute areas of fields and volumes of grain stores. Mathematics, for the Babylonians, was not abstract contemplation. It was infrastructure, and they were remarkably good at it. The Babylonians wrote on clay tablets, using a wedge-shaped stylus, pressing marks into soft clay that was then baked hard. Thousands of these tablets have survived, buried in the ruins of temples and scribal schools, preserved by the same dry climate that makes Iraq so hot today. And when modern scholars started deciphering these tablets in the 19th and 20th centuries, they were stunned by what they found. These weren't just records of grain shipments and tax receipts, though there were plenty of those. Many of them were mathematical texts, problem sets, reference tables, worked examples, the textbooks of Babylonian scribal schools. Students in ancient Mesopotamia actually did math homework on clay, and some of it was surprisingly sophisticated. The Babylonians had a full-fledged number system, and here's what's wild about it. They used base 60, not base 10, like we do. Base 60. 60 distinct digit positions before you roll over to the next place. Now, you might think that sounds insane. Who counts in 60s? But think about it. You already do, in certain ways. There are 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. All of those are Babylonian legacies, handed down through the Greeks and the Romans and the Arabs, and eventually to us. We're still using a 4,000-year-old number base every time we check the clock. And base 60 has some real advantages. 60 is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That's a lot of clean fractions. In base 10, 1/3 is an ugly repeating decimal, 0.3333, forever. In base 60, 1/3 is just 20 out of 60. Clean. Simple. The Babylonians chose well, and they didn't just count, they computed. We have tablets showing multiplication tables, tables of reciprocals, which they used for division, tables of squares and cubes. They could solve what we'd now call quadratic equations, problems involving unknowns raised to the second power. One famous tablet, known as YBC 7289, shows a square with its diagonal drawn in, and the numbers inscribed on it give the length of that diagonal to a remarkable degree of accuracy. Essentially, the square root of 2, correct to about 6 decimal places. This is from roughly 1800 BCE, nearly 4,000 years ago. Someone in Babylon was computing irrational numbers to 6-digit precision. Let that sink in for a second. Meanwhile, a few hundred miles to the west, the Egyptians were developing their own mathematical tradition along the Nile. Egyptian mathematics was less algebraic than Babylonian mathematics. They were more focused on practical geometry, which makes sense when you think about their needs. Every year, the Nile flooded, washing away boundary markers and reshaping the farmland along its banks. After the waters receded, surveyors had to go out and re-establish property lines, remeasure fields, recalculate areas. The Greek historian Herodotus actually claimed that geometry, the word literally means earth measurement, was invented in Egypt for exactly this reason. That's probably an oversimplification, but it captures something true. Egyptian geometry was born from the mud of the Nile. The best window we have into Egyptian mathematics is a document called the Rhind Papyrus, named after Alexander Henry Rhind, the Scottish antiquarian who purchased it in Luxor in 1858. The papyrus itself was written around 1550 BCE by a scribe named Ahmes, who tells us he's copying from an even older document, dating to perhaps 1850 BCE. It's basically a math textbook, 84 problems with solutions, covering arithmetic, fractions, geometry, and basic algebra. And it's fascinating, not just for what the Egyptians could do, but for how they thought about it. Here's an example. Egyptian fractions were weird by our standards. They almost exclusively used unit fractions, fractions with 1 in the numerator. So instead of writing 2/5, they'd write 1/3 plus 1/15. Instead of 3/4, they'd write 1/2 plus 1/4. Every fraction had to be decomposed into a sum of distinct unit fractions. It sounds cumbersome, and it kind of was, but it also meant they developed incredibly sophisticated techniques for manipulating these sums. There are problems in the Rhind Papyrus that involve dividing loaves of bread among workers using these unit fractions, and the solutions are clever and elegant, even if the notation feels alien to us. The Egyptians also had a pretty good approximation of pi, the ratio of a circle's circumference to its diameter. In one of the Rhind Papyrus problems, the area of a circle is calculated by taking the diameter, subtracting 1/9 of it, and squaring the result. If you work out what value of pi that implies, you get about 3.16, which is remarkably close to the actual value of roughly 3.14159. Not bad for nearly 4,000 years ago. And then there are the pyramids. You can't talk about Egyptian mathematics without talking about the pyramids, because whatever else they are, tombs, monuments, expressions of pharaonic power, they are also extraordinary feats of applied geometry. The Great Pyramid of Giza, built around 2560 BCE, has a base that's almost perfectly square. The 4 sides are each about 230 meters long, and the difference between the longest and shortest sides is less than 20 centimeters. The corners are almost perfect right angles. The whole structure is aligned to true north, with an accuracy of about 3/60ths of a degree. Think about what that means. We're talking about a structure that required the coordinated labor of tens of thousands of workers over roughly 20 years, involving millions of stone blocks, averaging about 2.5 tons each. And the whole thing is built with precision engineering tolerances that would be impressive in a modern construction project. They achieved this with copper tools, stone hammers, plumb bobs, and no concept of trigonometry as we know it. How they managed the alignment and the precision is still debated by archaeologists and engineers, but the precision itself is not in question. The numbers are in the stone. There's a document called the Moscow Papyrus, dating to around 1850 BCE, that contains a problem asking for the volume of a truncated pyramid, a pyramid with its top cut off. And the formula given is correct. It matches the formula you'd derive using integral calculus, which wouldn't be invented for another 3,000 years. How the Egyptians arrived at it is unclear. They didn't prove it. They didn't show their work, but they had it, and they used it. So by roughly 1500 BCE, you have 2 great mathematical traditions, Babylonian and Egyptian, both sophisticated, both practical, both driven by the needs of civilization. But neither of them had something that would turn out to be absolutely essential for mathematics to become what it eventually became. Neither of them had proof. They had procedures. They had algorithms. They had tables and formulas and worked examples. But they didn't have the idea that you could start from a set of basic assumptions and, through pure logical reasoning, demonstrate that a mathematical statement must be true, not just that it works in this case or that case, but that it's true always, everywhere, necessarily. That idea, the idea of mathematical proof, would come from somewhere else entirely. It would come from a rocky peninsula jutting into the eastern Mediterranean, a place where a new kind of thinking was about to be born. And the first person in that story, the first name that comes down to us through the fog of ancient history, as someone who proved a mathematical theorem, was a man from the city of Miletus, on the coast of what is now Turkey. His name was Thales, and he lived around 600 BCE, and the world he inhabited was about to change mathematics forever, in ways that neither the Babylonians nor the Egyptians could have imagined. Because Thales didn't just want to know that something was true, he wanted to know why. And that single shift in attitude, from what works to why it works, is arguably the most important intellectual leap in the entire history of mathematics. Now, we need to be a little careful here, because almost everything we know about Thales comes from writers who lived centuries after he did. He left no written works that survived, and the stories about him are a mix of history, legend, and philosophical embellishment. But the tradition is consistent on one point. Thales was the first person known to have proved geometric theorems using logical deduction rather than measurement or experience. He's credited with proving that a circle is bisected by its diameter, that the base angles of an isosceles triangle are equal, and that vertical angles formed by two intersecting lines are equal. These might sound obvious to you, and they are obvious, in a sense. But the point isn't the results. The point is the method. Thales wasn't saying, I measured a bunch of isosceles triangles, and the base angles always came out equal. He was saying, here's a logical argument that proves they must be equal, regardless of which triangle you're looking at. That's a completely different kind of knowledge. It's certain in a way that measurement can never be. And this idea, that you can know things with absolute certainty through reasoning alone, it electrified Greek intellectual life. Within a few generations, it had produced one of the most fascinating and influential movements in the history of thought, the Pythagorean school. Pythagoras of Samos. Born around 570 BCE on the island of Samos, off the coast of modern Turkey. He traveled widely as a young man. Tradition says he visited Egypt and Babylon and maybe even India, absorbing mathematical knowledge from older civilizations. Then, around 530 BCE, he settled in Croton, a Greek colony in what is now southern Italy, and founded something that was part philosophical school, part religious community, and part, honestly, cult. The Pythagoreans lived by strict rules. They were vegetarians, or at least most of them were. They had secret rituals and passwords. They believed in the transmigration of souls. And they were obsessed, truly, deeply obsessed, with numbers. The Pythagorean motto was, all is number. They believed that the fundamental nature of reality was mathematical. Not that mathematics described reality, but that mathematics was reality. Numbers weren't just tools for counting. They were the essence of existence itself. And they found evidence for this belief everywhere they looked. The most famous example is music. The Pythagoreans discovered that musical harmony is governed by simple numerical ratios. A string that's half as long produces a note 1 octave higher. A string 2/3 as long produces a perfect fifth. 3/4, a perfect fourth. The most pleasing harmonies correspond to the simplest ratios. This was, as far as we know, the first time anyone had found a precise mathematical law governing a natural phenomenon. The universe, at least in this one domain, really did seem to run on numbers. And of course there's the theorem, the Pythagorean theorem. In any right triangle, the square of the length of the hypotenuse equals the sum of the squares of the other two sides. A squared plus B squared equals C squared. You learned it in school. You've probably used it, maybe without even thinking about it. And here's the thing. The Babylonians knew this relationship. They had tablets listing Pythagorean triples, sets of 3 whole numbers that satisfy the equation, like 3, 4, 5 or 5, 12, 13, dating back to at least 1800 BCE. The Egyptians almost certainly used the 3, 4, 5 triangle as a practical tool for constructing right angles. But what the Pythagoreans did, or at least what tradition credits them with, was proving it. Not just observing that it works for these numbers and those numbers, but demonstrating, through logical argument, that it must work for every right triangle, always, everywhere, forever. And then the Pythagoreans discovered something that shook their worldview to its foundations, something so disturbing that, according to legend, they tried to keep it secret, and when one of their members revealed it to outsiders, he was, depending on which ancient source you believe, expelled from the community, or possibly drowned at sea. The discovery was this: not all numbers are rational. Here's what that means. A rational number is any number that can be expressed as a fraction, a ratio of 2 whole numbers, 1/2, 3/4, 7/3, -2/5, all rational. The Pythagoreans assumed that all quantities could be expressed this way. All is number, and all numbers are ratios. But consider a square with sides of length 1. By the Pythagorean theorem, the diagonal of that square has a length equal to the square root of 2. And someone, tradition often credits a Pythagorean named Hippasus, proved that the square root of 2 cannot be expressed as a ratio of 2 whole numbers. It's irrational. The proof is beautiful, by the way, and it's one of the oldest proofs by contradiction in existence. You assume the square root of 2 is rational. You write it as a fraction in lowest terms, and through a series of logical steps, you show that both the numerator and denominator must be even, which contradicts the assumption that the fraction was in lowest terms. Therefore, the assumption is false. The square root of 2 is not rational. It's something else, something new, something that doesn't fit in the Pythagorean framework. Think about what that meant for them. Their entire philosophy was built on the idea that reality is made of whole numbers and their ratios. And here was a number, not an exotic number, not some far-fetched abstraction, but the diagonal of a simple unit square, a shape a child could draw, that could not be expressed that way. The universe had cracks in it that their philosophy couldn't fill. It must have felt like the ground, shifting under their feet. And here's a nice irony. The discovery of irrational numbers was the first of many instances in the history of mathematics where the subject refused to stay within the boundaries people tried to set for it. Every time mathematicians said, "This is all there is," mathematics answered, "No, there's more." There are always more numbers, more structures, more truths than any framework can contain. That theme will come back again and again in our story tonight. But mathematics kept moving forward, as it always does, undaunted by philosophical crises. And the next great figure in our story is someone whose work was so comprehensive, so carefully constructed, so influential, that it shaped mathematical thinking for over 2,000 years. We know almost nothing about his personal life. No birth date, no death date, no biography, almost no anecdotes. He's one of the most important people who ever lived, and he's essentially a ghost. His name was Euclid, and he worked in Alexandria, Egypt, around 300 BCE, at the Great Library, the intellectual center of the ancient world, and he wrote a book called The Elements, or rather, a collection of 13 books, covering geometry, number theory, and mathematical reasoning. And here's the thing about The Elements. It's the most successful textbook in the history of the world. It was used continuously as the standard text for teaching geometry for more than 2 millennia. Abraham Lincoln studied it. It was still being used in British schools in the early 20th century. After the Bible, it's probably the most printed book in the Western world. What made the elements so extraordinary wasn't the individual results. Most of the theorems in it were already known. What made it extraordinary was the structure. Euclid started with a small set of definitions, postulates, and common notions, basic assumptions, that seemed self-evidently true. A point is that which has no part. A line is breadthless length. Through any 2 points, a straight line can be drawn. All right angles are equal. Things that are equal to the same thing are equal to each other. Starting from these simple foundations, Euclid built up the entire edifice of geometry, theorem by theorem, each one following logically from the ones before it. It was a masterpiece of logical architecture. Every result was proved. Every proof rested on earlier proofs, which rested on even earlier ones, all the way back to those basic postulates. Nothing was assumed without justification. Nothing was taken on faith. And one of those postulates, the 5th one, the so-called parallel postulate, would cause more intellectual anguish than any single mathematical statement in history. But that's a story for later. For now, what matters is the method. Euclid showed that you could build an entire mathematical universe from a handful of simple assumptions, using nothing but logical reasoning. That idea, the axiomatic method, is still the foundation of mathematics today. Every mathematical paper published in the 21st century is, in a deep sense, following the template Euclid laid down in Alexandria 2,300 years ago. But let's not leave ancient Greece without talking about one more person, because he might have been the greatest mathematician of the ancient world, and his story has one of the most dramatic endings in all of science. Archimedes of Syracuse. Born around 287 BCE, son of an astronomer, he spent most of his life in Syracuse, a Greek city-state on the island of Sicily. And Archimedes was extraordinary. He was extraordinary the way a Mozart or a Shakespeare is extraordinary, not just better than everyone else, but operating on a different level entirely. Archimedes figured out the principle of buoyancy, the famous Eureka moment, where he supposedly leaped from his bath and ran naked through the streets of Syracuse, having realized that a body immersed in fluid is buoyed up by a force equal to the weight of the fluid it displaces. He calculated the area under a parabola, using a method that was essentially integral calculus, nearly 2,000 years before Newton and Leibniz. He computed pi, to impressive accuracy, by inscribing and circumscribing polygons around a circle, starting with hexagons and doubling the sides again and again, 96-sided polygons, narrowing in on the value from above and below. He proved that the area of a circle equals pi times the radius squared. He found the surface area and volume of a sphere, a result he was so proud of that he asked for a sphere inscribed in a cylinder to be carved on his tombstone, and he did things with numbers that boggle the mind. In a work called The Sand Reckoner, Archimedes set out to prove that it was possible to express the number of grains of sand that would fill the entire universe. The point wasn't the answer. It was the fact that you could even ask the question. He had to invent a new notation for extremely large numbers, essentially creating a system of exponential arithmetic, because the existing Greek number system wasn't up to the task. He estimated the diameter of the universe using the best astronomical data available to him, assumed the sand grains were tiny, and calculated. The number he arrived at was about 10 to the 63rd power. What's remarkable isn't the number itself, it's the ambition, the willingness to apply mathematics to a question that seemed absurd, and to take it seriously. And then there's the war engineering. During the Roman siege of Syracuse, Archimedes turned his genius to defense. He designed catapults, calibrated to hit Roman ships at various ranges. Ancient sources describe mirrors or polished bronze shields used to focus sunlight and set ships on fire, the so-called heat ray, though modern historians debate whether that's legend or engineering fact. He may have designed a claw mechanism that could lift the prow of an attacking ship out of the water and then drop it. The Roman general Marcellus reportedly said that Archimedes was like a mythological hundred-handed giant, hurling projectiles at the Roman fleet with impossible accuracy. The siege dragged on for 2 years, largely because of Archimedes' inventions, but Syracuse fell in 212 BCE, according to the most famous version of the story, told by Plutarch, writing about 3 centuries later. A Roman soldier found Archimedes drawing geometric figures in the sand, absorbed in a problem. The soldier ordered him to come along. Archimedes refused, reportedly saying something like, "Do not disturb my circles." The soldier killed him. Marcellus had specifically ordered that Archimedes be kept alive and treated well. His reputation was that great, even among the enemy. Marcellus was reportedly furious and grieved when he learned of the death, but Archimedes was gone, and with him went the greatest mathematical mind the ancient world had produced. And here's the poignant thing. After Archimedes, Greek mathematics continued for several more centuries. There were important figures like Apollonius, who wrote the definitive work on conic sections, and Diophantus, who is sometimes called the father of algebra, and Hypatia of Alexandria, who was the last great mathematician of the ancient Greco-Roman world, before she was murdered by a mob in 415 CE. But the trajectory was downward. The Roman Empire, for all its engineering genius, aqueducts, roads, concrete, the Colosseum, had relatively little interest in abstract mathematics. They were practical people, builders and administrators, and they used mathematics as a tool without pushing it forward as a discipline. And as the Western Roman Empire crumbled in the 5th century, much of the Greek mathematical tradition was lost to Western Europe. Libraries were destroyed, texts were scattered. Knowledge that had taken centuries to build up was forgotten or preserved only in fragments. But it wasn't lost everywhere, and this is where the story takes a turn that many people in the West don't know as well as they should, because the next great chapter in the history of mathematics didn't happen in Europe at all. It happened in India, and one of the most important ideas in the entire history of human thought, an idea so fundamental that modern life would be literally impossible without it, came from the Indian subcontinent, and it took centuries to reach Europe. That idea is zero. Now, zero sounds like nothing, right? And in a way, that's exactly the point. Zero is the number that represents nothing. But the concept of nothing as a number, as a thing you can write down, manipulate, calculate with, treat as an equal citizen alongside 1 and 2 and 3, that's not obvious at all. It's actually deeply strange when you think about it. The Babylonians had a placeholder symbol to indicate an empty position in their number system, a way of distinguishing between, say, our equivalent of 302 and 32. But they never treated it as a number in its own right. The Greeks, for all their mathematical sophistication, didn't have zero either. They were uncomfortable with the very idea of nothingness having a numerical value. Aristotle argued against the concept of a void, and Greek mathematics was fundamentally geometric. They thought in terms of lengths and areas, and a length of zero didn't make geometric sense. But in India, the philosophical and mathematical climate was different. Indian thought had a long tradition of engaging with concepts of emptiness, void, and the infinite. The Sanskrit word for zero is shunya, which means empty or void, and it carries philosophical connotations that the Western mathematical tradition simply didn't have. And by the 5th century CE, Indian mathematicians were using 0 not just as a placeholder, but as a genuine number, a number you could add, subtract, and eventually multiply and divide with. The key figure here is Brahmagupta, who lived in the 7th century, working in Bilamala, a city in the northwest of India, in what is now Rajasthan. In 628 CE, Brahmagupta wrote a treatise called the Brahmasfuta Siddhanta, roughly translated as the correctly established doctrine of Brahma, and in it, he laid out the first known systematic rules for arithmetic with 0. He stated that any number plus 0 is that number, that any number minus itself is 0, that any number multiplied by 0 is 0. He even tackled division by 0, though he got that one wrong. He said 0 divided by 0 is 0, which modern mathematicians would disagree with. But the point is, he was treating 0 as a fully operational number, something you could compute with just like any other. That was revolutionary. And 0 wasn't the only contribution of Indian mathematics. Indian mathematicians developed the decimal place value system, the system we use every day, where the position of a digit determines its value. The digit 3 means 3 in the ones place, 30 in the tens place, 300 in the hundreds place. We take this so completely for granted that it's hard to see how revolutionary it was, but compare it to Roman numerals. Try multiplying max renmens v sieve. Good luck. The Roman system is fine for recording numbers, but it's terrible for computing with them. The Indian place value system, combined with 0 as a placeholder and a number, made arithmetic vastly more efficient. It was a technological breakthrough as significant as the printing press, and arguably more fundamental. And Brahmagupta wasn't working in isolation. Indian mathematics had a long and deep tradition by his time. Indian mathematicians also made remarkable progress in what we'd now call algebra and trigonometry. Aryabhata, working around 500 CE, more than a century before Brahmagupta, calculated pi to 4 decimal places, giving the value as 3.1416, and noted that it was an approximation, which shows a remarkable awareness that the exact value might be irrational. He developed sophisticated methods for solving systems of linear equations, used what we'd now call sine tables for astronomical calculations, and proposed that the Earth rotates on its axis, a fact that wouldn't be widely accepted in Europe for another 1,000 years. After Brahmagupta came Mahavira in the 9th century, who wrote the first textbook devoted entirely to mathematics rather than astronomy. Most earlier Indian mathematical works were embedded in astronomical treatises. And then there was Bhaskara II, in the 12th century, who anticipated some ideas of calculus and whose work on Diophantine equations was centuries ahead of anything being done in Europe. The word sine itself is actually the result of a bizarre chain of mistranslation. The Sanskrit word was jia, meaning bowstring, which was transliterated into Arabic as jiba, which was misread as jaib, meaning bay or fold, which was then translated into Latin as sinus, meaning curve or fold. From Sanskrit to Arabic to Latin to English, accumulating errors at every step. Mathematics is universal. Terminology is a mess. Now, here's where the story of Indian mathematics intersects with one of the other great intellectual traditions of the medieval world. Starting in the 7th century, the rapid expansion of Islam created a vast civilization stretching from Spain to Central Asia, and the rulers of this civilization, particularly the Abbasid caliphs in Baghdad, were enthusiastic patrons of learning. In the early 9th century, the Caliph Al-Ma'mun established the House of Wisdom in Baghdad, a major intellectual center where scholars translated Greek, Indian, and Persian texts into Arabic, preserved them, and built on them. This was one of the great acts of intellectual rescue in human history. Works by Euclid, Archimedes, Ptolemy, Aristotle, and many others that might otherwise have been lost were translated, studied, and extended by Arabic-speaking scholars. And it was here, in this extraordinary environment, that a mathematician named Muhammad ibn Musa al-Khwarizmi wrote 2 books that would shape the future of mathematics in ways he could never have predicted. The first, written around 820 CE, was a treatise on the Indian numeral system, essentially introducing the Hindu-Arabic numerals and the decimal place value system to the Islamic world. The second was called Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, the compendious book on calculation by completion and balancing. And from the title of that book, from the word al-Jabr, meaning completion or restoration, we get our word algebra. Now, what al-Khwarizmi was doing in this book wasn't algebra in the way we think of it today. He didn't use symbolic notation, didn't write equations with x's and y's. Everything was written out in words, but the methods were algebraic. He showed systematic procedures for solving linear and quadratic equations, organized by type, with proofs for each method. He was taking the ad hoc problem-solving techniques that the Babylonians and Indians had developed and organizing them into a coherent, teachable system. And here's a small but telling detail. Al-Khwarizmi's name, Latinized, became algorithmi, and from that name comes our word algorithm, a step-by-step procedure for solving a problem. Every algorithm running on every computer in the world today carries, in its name, the memory of a 9th century mathematician in Baghdad. The Indian Arabic mathematical tradition continued to develop for centuries after Al-Khwarizmi. Omar Khayyam, yes, the poet, the one who wrote the Rubaiyat, was also a brilliant mathematician who, in the 11th century, developed geometric methods for solving cubic equations and wrote a treatise on the difficulties of Euclid's definitions that showed remarkably modern thinking about the foundations of geometry. He also reformed the Persian calendar with such accuracy that it's more precise than the Gregorian calendar we use today. Other Islamic mathematicians made advances in number theory, combinatorics, and trigonometry that wouldn't be matched in Europe for centuries. Al-Haytham, in the 11th century, did groundbreaking work in optics, using mathematical methods that anticipated the scientific method itself. And in the 14th century, the Kerala School of Mathematics in southern India, working independently of both European and Islamic traditions, developed infinite series expansions for trigonometric functions that anticipated Taylor series by roughly 300 years. Mathematics was advancing on multiple fronts, across multiple civilizations, often in parallel and often without any awareness of what was happening elsewhere. But eventually, the mathematical knowledge of the Islamic world began flowing into Europe through the contact points, Spain, Sicily, the Crusader states. And the person who did more than anyone else to bring this mathematical revolution to European attention was a young Italian from Pisa who had traveled extensively in North Africa and the Eastern Mediterranean. His name was Leonardo of Pisa, though you almost certainly know him by his nickname, Fibonacci. And the book he published in 1202, the Liber Abaci, the Book of Calculation, would change the way Europe thought about numbers, because Fibonacci had seen the future, and the future was Hindu-Arabic numerals. Here's the situation in Europe at the beginning of the 13th century. Most calculations were still done using Roman numerals, or, more practically, using counting boards and abacuses. If you were a merchant in Pisa or Venice or Florence, and you needed to calculate the cost of a shipment of spices, you'd lay out tokens on a lined board and shuffle them around according to rules. It worked, but it was slow and cumbersome. Fibonacci had grown up partly in North Africa. His father was a customs official in the Almohad dynasty port of Bugia, in what is now Algeria, and there he'd learned the Hindu-Arabic numeral system from Arab merchants and mathematicians. He immediately saw how much more powerful it was. The Liber Abaci didn't just introduce the numerals. It showed how to use them for practical calculation, for commerce, for currency conversion, for the kinds of problems that merchants and traders actually faced. And buried in its pages was a little puzzle about rabbit populations that would make Fibonacci's name immortal, even though it was a tiny footnote in a massive book. You start with one pair of rabbits. Each month, every mature pair produces a new pair. How many pairs do you have after 12 months? The answer generates a sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, where each number is the sum of the two before it, the Fibonacci sequence. And this sequence turns out to appear everywhere in nature, in the spirals of sunflower seeds, in the branching of trees, in the proportions of seashells. The ratio of consecutive Fibonacci numbers converges on the golden ratio, about 1.618, which appears in art, architecture, and geometry. Fibonacci almost certainly didn't know any of this. For him, it was just a fun puzzle about rabbits. But mathematics has a way of connecting things you'd never expect. Now, the spread of Hindu-Arabic numerals through Europe was slow. It took centuries, not years. Many people resisted the new system. There were actually laws passed in Florence in 1299 banning the use of Arabic numerals in official documents, partly because the symbols were unfamiliar and partly because they were seen as easier to forge than Roman numerals. Old habits die hard, but by the 15th and 16th centuries, the transition was essentially complete, and European mathematics was poised for an explosion of creativity that would transform the subject beyond recognition. And to understand that explosion, we need to talk about the strangest mathematical drama of the 16th century, the battle over the cubic equation. This is a story with everything: secret formulas, public challenges, betrayal, poetry, and the birth of a whole new kind of number. It starts in early 16th century Italy, in a world where mathematics was not just an academic pursuit, but a form of intellectual combat. Here's how it worked. In Renaissance Italy, mathematicians held public contests. You'd challenge a rival, each of you would pose a set of problems, and whoever solved more would win, along with prize money, prestige, and sometimes a university appointment. Your mathematical knowledge wasn't just scholarship, it was your livelihood, and that meant there was a powerful incentive to keep your methods secret. The central figure in this drama is Niccolò Fontana, better known by his nickname Tartaglia, the stammerer. As a child in Brescia, he'd been slashed across the face with a sword during a French raid in 1512, leaving him with a speech impediment and terrible scars. He grew up poor, largely self-taught, and became one of the most formidable mathematicians in Italy. And sometime around 1535, Tartaglia figured out how to solve the depressed cubic equation, a cubic equation without a squared term. This was a big deal. Quadratic equations had been solved since the Babylonians, but cubics had resisted every attack for thousands of years, and Tartaglia cracked it. He kept his method secret, naturally, because it was his competitive advantage. But then along came Girolamo Cardano, a physician, mathematician, gambler, astrologer, and all-around Renaissance character who was writing an ambitious algebra textbook. Cardano begged Tartaglia for the solution, swearing a solemn oath never to publish it. Tartaglia eventually relented, sharing the method in the form of a cryptic poem. Yes, a poem, because obscurity was a form of intellectual property protection. Cardano took the method, worked with it, extended it, had his brilliant student Lodovico Ferrari figure out how to solve the quartic equation, the fourth degree, and then discovered that another mathematician, Scipione del Ferro, had actually solved the cubic before Tartaglia. Armed with this justification, del Ferro had priority, so Tartaglia's secret wasn't really Tartaglia's to keep. Cardano published everything in his 1545 masterpiece, the Ars Magna. Tartaglia was furious. He accused Cardano of oath-breaking. A bitter public feud erupted, with challenges and counter-challenges and personal insults. It was ugly and petty and very human. But the mathematics in the Ars Magna was extraordinary. And here's the thing that makes this story so important for the long run. When Cardano and his collaborators worked through the cubic formula, actually applying it to specific equations, they kept running into situations where the formula required them to take square roots of negative numbers, the square root of -1. And in the real world, there's no number that, multiplied by itself, gives a negative result. 2 times 2 is 4. -2 times -2 is also 4. There's nothing that squares to give you -1. Cardano called these numbers sophistic, and as subtle as they are useless. He had no idea what they meant. But he noticed something remarkable. If he just pretended these square roots of negative numbers were real, if he went ahead and did arithmetic with them, plugging them into the formula and carrying through the calculations, the imaginary parts would cancel out at the end, and he'd be left with perfectly real, correct answers. The impossible numbers were a detour through nonsense that somehow led to truth. These impossible numbers would eventually be called imaginary numbers, and later, complex numbers, and they would turn out to be not useless at all, but absolutely essential to mathematics and physics. They're fundamental to electrical engineering, to quantum mechanics, to fluid dynamics, to signal processing. Every time you use a phone, a computer, or anything powered by alternating current, complex numbers are involved in the engineering behind it. The square root of -1, that thing Cardano called sophistic and useless, turned out to be one of the most important numbers in all of mathematics. But that realization would take another 300 years. Let's keep moving through the 16th and 17th centuries, because the pace is picking up now, and the ideas are getting bigger. In France, a lawyer named Pierre de Fermat was spending his spare time revolutionizing mathematics. Fermat was an amateur in the best sense. He had a full-time job as a legal counselor in the Parlement of Toulouse, which was essentially a judicial body, and he did mathematics for the pure love of it, in his evenings and on his time off. And he was devastatingly good. He made foundational contributions to number theory, analytic geometry, optics, and probability. He also independently developed many of the ideas that would become calculus, finding methods to compute tangent lines and areas under curves that anticipated Newton and Leibniz by decades, though he never pulled it all together into a unified framework. Meanwhile, René Descartes, yes, the "I think, therefore I am" philosopher, was doing something revolutionary of his own. In 1637, he published La Géométrie, in which he showed how geometric problems could be translated into algebraic equations and solved with algebra. This was the birth of coordinate geometry, the idea that you can describe any point in a plane by 2 numbers, its x and y coordinates, and that curves and shapes could be described by equations. The straight line becomes y equals mx plus b. The circle becomes x squared plus y squared equals r squared. Geometry and algebra, which had been separate streams of mathematics for 2,000 years, were unified into a single powerful framework. Every time you see a graph, in a textbook, in a spreadsheet, on a dashboard, you're using Descartes' idea. The story of how Fermat and Blaise Pascal essentially invented probability theory through their correspondence about gambling problems in 1654 is wonderful. 2 brilliant minds working out, through letters, the mathematics of uncertainty. starting from a question posed by a professional gambler named Antoine Gombeau, known as the Chevalier de Marais. The question was about how to fairly divide the stakes in an interrupted dice game. If two players are in the middle of a game and have to stop, how should the prize money be split based on their current positions? The answer required a completely new kind of mathematical thinking, reasoning not about what is true, but about what is likely. Probability theory, the mathematics of chance. It would go on to become one of the most practically important branches of mathematics, underpinning statistics, insurance, finance, genetics, physics, artificial intelligence, and the entire scientific method. All from a question about dice. But Fermat is most famous for something he didn't do, or at least something he claimed to have done but never showed. In the margin of his copy of Diophantus's Arithmetica, next to a discussion of the Pythagorean theorem, Fermat wrote a note. He said that the equation x to the n plus y to the n equals z to the n has no whole number solutions when n is greater than 2. For n equals 2, you get Pythagorean triples, 3, 4, 5, 5, 12, 13, infinitely many solutions. But for n equals 3, or 4, or any higher power, Fermat claimed there are no solutions at all. And then he wrote one of the most infuriating sentences in the history of mathematics. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. That marginal note, Fermat's last theorem, as it came to be called, would torment mathematicians for 358 years. Did Fermat really have a proof? Almost certainly not, at least not a correct one, because the eventual proof would require mathematical machinery that wouldn't be invented until the 20th century. But the problem itself, so simple to state and so maddeningly difficult to solve, became the most famous unsolved problem in mathematics. We'll come back to it, I promise. Meanwhile, something enormous was brewing, something that would transform not just mathematics, but all of science. Two men, working independently, on different sides of the English Channel, were about to invent the most powerful mathematical tool ever created, and their bitter, ugly, decades-long fight over who deserved credit would become one of the nastiest priority disputes in the history of science. The tool was calculus, and the two men were Isaac Newton and Gottfried Wilhelm Leibniz. And to understand why calculus mattered so much, you first need to understand the problem it solved. Here's the thing. By the mid-17th century, science was exploding. Galileo had shown that falling bodies accelerate. Kepler had worked out the shapes of planetary orbits. Huygens was studying pendulums and waves. Everywhere people looked, they saw things changing, objects moving, populations growing, curves sweeping through space. And the mathematics they had wasn't good enough to handle change. Greek geometry was static. It dealt with fixed shapes, circles, triangles, spheres. Algebra dealt with fixed equations. But the natural world is dynamic. Things move. They speed up and slow down. They grow and shrink. Areas accumulate. Curves bend. The rate at which something happens is itself constantly changing. The existing mathematical toolkit couldn't capture this. It was like trying to photograph a galloping horse with a paintbrush. You needed something that could handle motion, change, and the infinite. That something was calculus. And the basic idea, let me try to give you the intuition, because the intuition is beautiful, is this. Imagine you're driving a car, and you want to know your exact speed at one precise instant. Not your average speed over an hour or a minute. Your speed right now, at this exact moment. How would you calculate that? Well, speed is distance divided by time. So you could measure how far you travel in 1 second and divide by 1 second. But that gives you an average over that second, not an instantaneous speed. What if you measured over half a second, a tenth of a second, a thousandth? The shorter the time interval, the closer your average speed gets to your true instantaneous speed. Calculus says, take the limit, let the time interval shrink towards zero, and see what the average speed approaches. That limiting value is your instantaneous velocity. That process of taking a limit, of dividing an infinitely small change in distance by an infinitely small change in time, is called differentiation. It gives you the rate of change of any quantity at any instant, and there's a mirror image process. If differentiation tells you the rate at which something is changing, integration does the reverse. It accumulates. If you know the speed of a car at every instant, integration lets you add up all those instantaneous speeds to figure out the total distance traveled. It's like adding up infinitely many, infinitely thin slices to get a total area, or a total volume, or a total anything. And the stunning thing, the thing that ties the whole subject together, is that differentiation and integration are inverses of each other. They undo each other. This is called the fundamental theorem of calculus, and it's one of the most beautiful and consequential results in all of mathematics. Now, Isaac Newton figured most of this out between 1665 and 1667, when he was in his early 20s. Cambridge University had closed because of the plague, the Great Plague of London, which swept through England killing roughly 100,000 people, and Newton retreated to his family home in Woolsthorpe, a small village in Lincolnshire. He was 23. No degree yet, no position, no reputation. Just a young man with an extraordinarily powerful mind and, suddenly, nothing to do but think. And there, in isolation, in a quiet farmhouse in the English countryside, while plague raged through the cities, over the course of about 2 years, he invented calculus, discovered the laws of motion, formulated his theory of universal gravitation, and did foundational work on optics, including his famous experiments with prisms, showing that white light is composed of a spectrum of colors. It might be the most productive period any single human being has ever had. Newton himself, looking back on it years later, wrote, "In those days, I was in the prime of my age for invention and minded mathematics and philosophy more than at any time since." The understatement is staggering. Newton called his version of calculus the method of fluxions, fluxions being his term for rates of change, which he imagined as quantities flowing and changing over time, like a moving point tracing out a curve, and he used it to solve problems that had baffled mathematicians for generations. Areas under curves, tangent lines, maxima and minima, the motion of bodies under gravity, all of it yielded to this new tool. He eventually published his masterwork, the Principia Mathematica, in 1687, and in it, he used his new mathematics to derive the laws of planetary motion from his law of universal gravitation. Kepler had described the elliptical orbits of the planets empirically. Newton explained why they were elliptical. It was one of the greatest triumphs of human reasoning, showing that the same force that makes an apple fall from a tree also holds the moon in orbit around the Earth, and the Earth in orbit around the Sun. One law governing everything from falling raindrops to the movements of galaxies. But Newton didn't publish. He was secretive, prickly, and paranoid about his ideas being stolen. He circulated manuscripts among a few close contacts, but kept the method of fluxions largely to himself for decades. And meanwhile, completely independently, Gottfried Wilhelm Leibniz, a German polymath working in Hanover, developed his own version of calculus in the mid-1670s. Leibniz was everything Newton wasn't in temperament. Where Newton was reclusive and suspicious, Leibniz was sociable and collegial. Where Newton hoarded his results, Leibniz published promptly. And crucially, Leibniz developed a notation, the familiar dx, dy, the integral sign, that was far more intuitive and flexible than Newton's dots and primes. It's Leibniz's notation we still use today. For a while, things were cordial. Newton and Leibniz exchanged letters. There was mutual, if guarded, respect. But by the late 1690s, the priority dispute had begun to fester. Partisans on both sides started making accusations. Newton's supporters claimed Leibniz had stolen the ideas from Newton's unpublished manuscripts, which Leibniz had briefly seen during a visit to London in 1676. Leibniz's supporters claimed independent invention, pointing out that Leibniz's approach was conceptually different and his notation was clearly superior. The fight got vicious. In 1712, the Royal Society in London convened a commission to adjudicate the dispute. Newton was president of the Royal Society at the time, and he secretly wrote the commission's report himself, a report that concluded, unsurprisingly, that Newton had priority. Leibniz was outraged, and rightly so. The proceedings were about as fair as a trial where the plaintiff is also the judge. He spent his final years defending his reputation, and when he died in 1716, he died largely alone, without the honors he deserved. Newton, for his part, reportedly said he had broken Leibniz's heart, and there's evidence he wasn't displeased by this. The dispute consumed the last years of both their lives and poisoned relations between British and continental mathematics for nearly a century. British mathematicians stubbornly stuck with Newton's inferior notation out of national loyalty, while continental mathematicians, particularly the Bernoulli family in Switzerland and their brilliant students, used Leibniz's much more practical die dx notation and surged ahead. The Swiss, French, and German mathematical traditions flourished throughout the 18th century. British mathematics stagnated. It was a tragedy, really. Their greatest genius's pettiness cost them a century of progress. It wasn't until the early 19th century that British mathematicians finally swallowed their national pride and adopted Leibniz's notation. But here's the thing that matters for the long view. Whether you credit Newton or Leibniz or both, and modern historians generally credit both, as genuine independent inventors, calculus changed everything. Before calculus, scientists could describe the world in static snapshots. After calculus, they could describe how the world changes. They could write down the laws of physics as differential equations, equations involving rates of change, and solve them to predict the future behavior of any system, the trajectory of a cannonball, the orbit of a planet, the flow of heat through a metal bar, the vibration of a violin string, the growth of a population. All of this became mathematically tractable once you had calculus. It was the language the universe had been waiting for, and the person who did more than anyone else to develop that language, to push calculus to its limits and invent vast new territories of mathematics along the way, was someone who was born just 20 years after Newton published his Principia. His name was Leonhard Euler, and by any reasonable measure, he is the most prolific mathematician who has ever lived. But Euler deserves a slow introduction, because his story is one of those remarkable tales of sheer intellectual output that almost defies belief. Born in Basel, Switzerland in 1707, Euler showed extraordinary mathematical talent from childhood. His father, a pastor, had studied under Johann Bernoulli, one of the leading mathematicians of the era, and Bernoulli himself quickly recognized the boy's gifts. By the time Euler was in his late teens, he was already publishing original mathematical work. He moved to St. Petersburg, Russia, at 20, to join the newly founded Russian Academy of Sciences, and he spent most of his career there and in Berlin, producing mathematics at a rate that has never been equaled. The numbers are staggering. Euler published over 800 papers and books during his lifetime, and his collected works, the Opera Omnia, fill over 70 volumes. It's estimated that he was responsible for roughly 1/3 of all the mathematical and scientific output of the 18th century. That's not a typo. 1/3. And the range of topics was as astonishing as the volume. He made fundamental contributions to calculus, number theory, graph theory, mechanics, optics, astronomy, fluid dynamics, and music theory. He invented much of the notation we use today. The letter E for the base of the natural logarithm, the letter I for the square root of -1, the symbol pi for the ratio of a circle's circumference to its diameter, the sigma symbol for summation, the function notation f of x. Before Euler, mathematical writing was a tangled mess of inconsistent symbols. After Euler, it looked more or less like it does today, and there are delightful stories about Euler that tell you something about the man. He once settled an argument at the court of Catherine the Great in Russia by scribbling a formula and announcing that algebra proved God existed. The philosopher Denis Diderot, who was his opponent and who knew no mathematics, was so flustered that he left court the next day. It's probably apocryphal, or at least exaggerated, but it captures something true about Euler's character. Mathematics was, for him, the answer to everything. He also essentially invented graph theory in a single paper. In 1736, the city of Königsberg had 7 bridges connecting 2 islands and the mainland, and the locals had a puzzle. Could you walk through the city, crossing each bridge exactly once? Euler proved it was impossible, and in doing so, he created an entirely new branch of mathematics, the study of networks, connections, and paths. That same branch of mathematics now underlies everything from GPS routing to social media algorithms, to the design of computer chips. And here's what makes Euler even more remarkable. In 1738, he lost vision in his right eye, possibly from an infection, possibly from a strain from staring at the sun during astronomical observations. He continued working without pause. In 1766, cataracts destroyed the vision in his remaining eye. He was essentially blind for the last 17 years of his life, and his productivity actually increased. He had a phenomenal memory. He could recite the entire Aeneid from memory, specifying the first and last lines of every page of the edition he'd read, and he could perform enormous calculations in his head. He dictated his papers to assistants, sometimes composing complex mathematical arguments purely mentally, holding the entire structure of a proof in his mind, without writing anything down. When he died in 1783, reportedly while calculating the orbit of a newly discovered planet and drinking tea, before suddenly saying, "I am dying," and collapsing, he was so far ahead of the rest of the mathematical world that papers he'd written years earlier were still being published posthumously for nearly 50 years after his death. One result of Euler's deserves special mention because it's been called the most beautiful equation in mathematics, and it connects 5 of the most important numbers in the subject in a way that feels almost magical. It's Euler's identity. E to the power of I times pi plus 1 equals 0. That's it. The base of the natural logarithm, the imaginary unit, the ratio of a circle to its diameter, the additive identity, and the multiplicative identity, 5 numbers from completely different areas of mathematics, linked together in one compact equation. When the physicist Richard Feynman first encountered it as a teenager, he called it the most remarkable formula in mathematics. There's no reason, intuitively, why these 5 quantities should be related, and yet they are. That's the kind of thing that makes mathematicians believe there's a deep, hidden order to the mathematical universe, a structure that we discover rather than invent. Now, let's move forward to the early 19th century, because 2 of the most important, and most dramatically different, stories in mathematics are about to unfold. One involves a quiet, careful German who became arguably the greatest mathematician since Archimedes. The other involves a hot-tempered French teenager who died in a duel at 20, leaving behind a few pages of scrawled notes that would reshape the entire landscape of algebra. The German was Carl Friedrich Gauss. Born in 1777 in Brunswick to a poor family, his father was a gardener and bricklayer. Gauss was a prodigy of almost unbelievable precocity. The most famous story, which may be embellished but is almost certainly based on truth, is that at the age of 7 or 8, his schoolteacher, trying to keep the class busy, asked the students to add up all the numbers from 1 to 100. Gauss produced the answer almost immediately. He'd seen the trick. You pair the first number with the last. 1 plus 100 is 101. 2 plus 99 is 101, and so on. 50 pairs, each summing to 101, giving 5,050. The teacher was stunned. The Duke of Brunswick heard about the prodigy and became his patron, funding Gauss's education through university and beyond. Gauss's contributions are so numerous that listing them feels inadequate, but let me try. In number theory, he published the Disquisitiones Arithmeticae in 1801, at the age of 24, a book that is still considered one of the masterpieces of mathematical literature. In it, he developed modular arithmetic, proved the law of quadratic reciprocity, and established the theory of quadratic forms. He also proved, in that same book, exactly which regular polygons can be constructed with compass and straight edge alone, a question that had been open since the Greeks. At the age of 19, before the book was even published, he'd shown that the regular 17-sided polygon, the heptadecagon, could be constructed with compass and straight edge. Nobody had known this was possible. It was a result of such unexpected beauty that Gauss reportedly considered it one of his finest achievements and requested that a 17-sided polygon be carved on his tombstone. The stonemason declined, saying it would be indistinguishable from a circle. That same year, 1801, Gauss performed another feat that made him famous across Europe. The asteroid Ceres had been discovered on January 1st by Giuseppe Piazzi, but after 41 days of observation, it disappeared behind the glare of the sun. Astronomers had too little data to compute its orbit using the existing methods. Gauss invented a new method, essentially developing what we now call least squares fitting, and predicted where Ceres would reappear months later. When astronomers pointed their telescopes to his predicted position, there it was, almost exactly where he'd said it would be. He was 24 years old. He did foundational work in statistics. The bell curve is also called the Gaussian distribution. He co-invented the electric telegraph with Wilhelm Weber. He made deep contributions to differential geometry that would later prove essential for Einstein's general relativity. And he made contributions to non-Euclidean geometry that he kept to himself for decades, apparently afraid of the controversy they might cause. And that last point, the geometry, is where things get really interesting. Remember Euclid's fifth postulate, the parallel postulate? It says, in essence, that through a point not on a given line, there is exactly one line parallel to the given line. For over 2,000 years, mathematicians had tried to prove this postulate from the other four, to show that it was a necessary consequence of the more basic axioms, rather than an independent assumption. Nobody could do it. They kept failing, generation after generation. And the reason they kept failing is that the parallel postulate is independent of the other axioms. You can't prove it. And you can have consistent geometries where it's false. Gauss realized this probably by the 1810s or 1820s, but he never published. He was cautious, conservative, reluctant to invite controversy. He once wrote that he feared the clamor of the Boeotians, referring to a Greek people known for their supposed dullness. The first mathematicians to actually publish non-Euclidean geometries were Nikolai Lobachevsky, a Russian, in 1829, and János Bolyai, a Hungarian, around the same time. Lobachevsky's geometry assumed that through a point not on a line, you could draw infinitely many lines parallel to the given line. Bolyai's was essentially equivalent. Both men constructed complete, self-consistent geometric systems in which Euclid's parallel postulate was false. When Bolyai's father sent his son's work to Gauss, hoping for encouragement, Gauss replied that he couldn't praise the work because it would be like praising himself. He'd already discovered the same things. Bolyai was crushed. He never published significant mathematics again. Think about what non-Euclidean geometry means, though. For 2,000 years, Euclid's geometry wasn't just mathematics. It was truth. It was the geometry of physical space, the geometry of the world you live in. The philosopher Immanuel Kant had argued that Euclidean geometry was a necessary feature of human cognition, something built into the very way our minds organize experience. It wasn't empirical. It was a priori, known before experience, certain by the nature of thought itself. And now here were mathematicians showing that you could have perfectly logical, perfectly consistent geometries, where parallel lines behaved differently, where the angles of a triangle didn't add up to 180 degrees, where the whole spatial universe could have a fundamentally different shape. If Kant was right that we know Euclidean geometry innately, then what did it mean that alternative geometries were logically possible? It was a profound philosophical shock, and it reverberated far beyond mathematics. If geometry wasn't necessarily about the real world, what was mathematics about? Were mathematical truths discoveries about an external reality, or were they inventions, games played with axioms that could be changed at will? That question is still debated today, and it's one of the deepest in the philosophy of mathematics. And it turned out that non-Euclidean geometry wasn't just an abstract curiosity. When Einstein developed his general theory of relativity in 1915, he needed exactly this kind of geometry to describe how mass curves space-time. The geometry of the universe, it turns out, really is non-Euclidean. Euclid's parallel postulate is approximately true for everyday distances. The curvature of space-time is too slight to notice when you're measuring rooms and roads, but on cosmic scales, space curves. The mathematics that Gauss was afraid to publish, and that Bolyai and Lobachevsky developed in obscurity, turned out to be the language of gravity itself. Now, the French teenager, Évariste Galois. His story is one of the most tragic in all of mathematics, and it's been romanticized almost to the point of myth, so let me try to tell it carefully. Galois was born in 1811, near Paris. He was brilliant and hot-headed, a combination that would serve him badly. He discovered his passion for mathematics in his mid-teens and quickly moved to the frontier of the subject. At 17, he submitted a paper to the French Academy of Sciences. It was lost. He submitted another paper. It was rejected. He applied twice to the École Polytechnique, France's most prestigious school for mathematics. He was rejected both times, partly because his verbal explanations were apparently too terse and impatient for the examiners, who couldn't follow his leaps of reasoning. He finally entered the less prestigious École Normale, where he was eventually expelled for writing a political letter that was deemed inflammatory. He was a fervent Republican in an era of monarchist restoration, and he was twice arrested for political activities. He was 20 years old, and in the margins and notebooks and hurried letters of this brief, turbulent life, Galois developed an entirely new branch of mathematics. What he did was this. He found a way to determine whether a polynomial equation can be solved by a formula, whether you can write down an expression involving the coefficients using only addition, subtraction, multiplication, division, and root extraction that gives you the solutions. Quadratic equations have the quadratic formula. Cubics and quartics have their formulas, discovered by Tartaglia and Ferrari. But what about quintic equations, fifth degree and higher? A Norwegian mathematician named Niels Henrik Abel had already proved, in 1824, that there is no general formula for solving quintic equations. But Abel's proof only told you it couldn't be done. It didn't tell you why, and it didn't tell you which specific quintic equations could be solved by formula and which couldn't. Galois cracked that problem by inventing what we now call group theory, the study of symmetry in its most abstract and general form. He showed that whether an equation is solvable depends on the symmetry properties of its roots, captured by a mathematical structure now called the Galois group. If the Galois group has a certain property, if it's what mathematicians call solvable, then the equation has a formula. If not, it doesn't. It was a stunning achievement, connecting the solvability of equations to abstract symmetry in a way nobody had imagined. On the night of May 29, 1832, Galois was in despair. He was facing a duel the next morning. The exact circumstances are murky, but it seems to have involved a love affair and a point of honor. He may have believed he would die, and so he stayed up all night, frantically writing out his mathematical ideas in a letter to his friend Auguste Chevalier. In the margins, he scrawled desperate notes. "I have not time," and "There is something to complete in this proof." He was trying to get his ideas down before it was too late. The next morning, May 30th, 1832, Galois was shot in the abdomen in the duel. He was left lying in the field. A passing peasant found him and took him to a hospital, where he died the following day, on May 31st. He was 20 years old. His manuscripts were eventually published more than a decade later, and mathematicians spent the next several decades working out what he'd actually meant. The ideas turned out to be extraordinarily deep. Group theory, which Galois essentially invented, became one of the central organizing principles of modern mathematics. It's the mathematics of symmetry, not just the symmetry of shapes and patterns, but the symmetry of equations, of physical laws, of the fundamental structure of the universe. When physicists today talk about symmetry groups governing the fundamental forces of nature, they're speaking a language that traces directly back to a desperate young man riding through the night before his death. And here's the thing that connects Galois to the broader story we're telling. Mathematics in the 19th century was undergoing a transformation that went far beyond any individual result. It was becoming more abstract, more concerned with structure than with calculation, more interested in the relationships between mathematical objects than in the objects themselves. The shift from "what is the answer to this equation" to "what kind of equation is this, and what does its structure tell us?" That's the shift from classical to modern mathematics. And it was happening everywhere at once. In geometry, with the discovery of non-Euclidean spaces. In algebra, with group theory. In analysis, with the rigorous foundations being laid by Augustin Louis Cauchy, Karl Weierstrass, and others for calculus, which had been operating for 2 centuries on brilliant but logically shaky intuitions. Newton and Leibniz had used infinitesimals, infinitely small quantities, without really defining what they were. It worked, spectacularly, but it was mathematically sloppy. The 19th century cleaned it up, replacing vague talk of infinitesimals with the precise language of limits, epsilons, and deltas. It made calculus rigorous. It made it safe. And there was Bernhard Riemann, who in 1854, at the age of 27, delivered a lecture in Göttingen that quietly revolutionized both mathematics and physics. It was his Habilitationsschrift, essentially his job talk, and the topic, suggested by Gauss himself, was the foundations of geometry. In that single lecture, Riemann laid out a vision of geometry so general, so flexible, so far ahead of its time, that it would take 60 years for physics to catch up. He described curved spaces of any number of dimensions, spaces whose curvature could vary from point to point, spaces that didn't need to be embedded in any larger flat space. He gave mathematics the tools to describe geometries that Euclid couldn't have imagined. And when Einstein needed a mathematical framework for general relativity, for describing how mass curves space-time, it was Riemann's geometry he reached for. The lecture hall in Göttingen, where a nervous young mathematician stammered through his ideas about curved space, turned out to be the birthplace of the mathematical language of gravity. But perhaps the most dramatic transformation of the 19th century, and the one with the deepest consequences for the foundations of mathematics itself, involved something that had haunted the subject since the very beginning, the concept of infinity. And the person who finally tamed infinity, or tried to, was a mathematician named Georg Cantor, and his story is one of the most extraordinary and heartbreaking in all of mathematics. Cantor was born in 1845 in St. Petersburg, Russia, to a family of German descent. He grew up in Germany, studied mathematics at some of the best universities in Europe, and by his late 20s, he was working at the University of Halle, a respectable but not prestigious institution. And there, in the 1870s and 1880s, he began developing a theory that would shake the foundations of mathematics and nearly destroy him in the process. The theory was about infinity. Now, infinity had always been a troublesome concept. The ancient Greeks, by and large, avoided it. Aristotle distinguished between potential infinity, a process that could continue without end, like counting, and actual infinity, a completed, existing infinite collection. He accepted the former and rejected the latter, and for over 2,000 years, most mathematicians followed his lead. Infinity was a useful shorthand for as large as you want, but nobody treated it as a genuine mathematical object. Cantor changed that. He developed what we now call set theory, and he used it to show something that even now, when you first hear it, sounds impossible. He showed that there are different sizes of infinity, not just one infinity, but an endless hierarchy of infinities, each one larger than the last. Here's the key idea. Two sets have the same size. Cantor said they have the same cardinality, if you can pair up their elements one to one. Every element in the first set gets matched to exactly one element in the second, and vice versa. For finite sets, this is obvious. A set of 3 apples and a set of 3 oranges have the same size because you can pair each apple with one orange. But Cantor applied this idea to infinite sets, and the results were astonishing. Consider the natural numbers, 1, 2, 3, 4, and so on, an infinite set. Now consider the even numbers, 2, 4, 6, 8, and so on, also infinite. But surely there are more natural numbers than even numbers, right? After all, the even numbers are a subset. Every even number is a natural number, but not every natural number is even. And yet Cantor showed that these two sets have the same cardinality. You can pair them up perfectly. 1 goes with 2, 2 goes with 4, 3 goes with 6, 4 goes with 8, and so on. Every natural number gets matched with exactly one even number, and vice versa. No leftovers. The two infinite sets are, in Cantor's precise sense, the same size. An infinite set can be the same size as a proper subset of itself. That's wild. That's counterintuitive. And that's what infinity does. But here's where it gets really strange. Cantor then asked, are all infinite sets the same size? And the answer is no. He proved, with an argument so elegant it takes your breath away, that the real numbers, the set of all points on a number line, are strictly more numerous than the natural numbers. You cannot pair them up one to one. there will always be real numbers left over, unmatched, no matter how clever your pairing scheme is. The proof is called Cantor's diagonal argument, and it's one of the most famous proofs in all of mathematics. Here's the basic idea. Suppose you could list all the real numbers between 0 and 1 in an infinite list. Each one is an infinite decimal, 0.314159, 0.271828, 0.50000, and so on. Now, construct a new number by looking at the diagonal. Take the first digit after the decimal point of the first number, the second digit of the second number, the third digit of the third number, and so on. You now have a sequence of digits. Change each one. If it's a 5, make it a 6. If it's anything else, make it a 5. Whatever rule you like. This gives you a new decimal number, and this new number is guaranteed to differ from every number on your list. It differs from the first number in the first decimal place, from the second number in the second decimal place, and so on. It's a real number that's not on your list, so your list wasn't complete. And this works no matter what list you started with. Therefore, the real numbers can't be listed. They're uncountable. They represent a strictly larger infinity than the natural numbers. Think about what that means. There are more numbers between 0 and 1, between your thumb and your index finger, if they're an inch apart, than there are whole numbers in the entire infinite sequence, 1, 2, 3, 4, stretching on forever. The continuum, the smooth number line, is richer, denser, more populous than the discrete infinity of the counting numbers. It's a bigger infinity, genuinely, provably, inescapably bigger. And it doesn't stop there. Cantor showed there's a whole tower of bigger and bigger infinities beyond that, each one constructed from the one before by taking its power set, the set of all possible subsets. The power set of the natural numbers is bigger than the natural numbers. The power set of that is bigger still, and so on, forever. There is no biggest infinity. The hierarchy of infinities is itself infinite. It's infinities all the way up, with no ceiling, no endpoint, no largest. If that makes your head spin a little, you're in excellent company. It made a lot of professional mathematicians' heads spin too. Now, you might think this would be celebrated as a triumph of pure thought, and eventually it was. But at the time, Cantor's work provoked fierce opposition. His former teacher, Leopold Kronecker, was the most vocal critic. Kronecker believed that mathematics should be founded on the natural numbers and constructive methods. He rejected the idea of actual infinity, rejected the existence of irrational numbers as legitimate mathematical objects, and reportedly called Cantor a corrupter of youth. He blocked Cantor's publications and tried to prevent him from getting positions at more prestigious universities. Cantor spent his entire career at Halle, never getting the appointment at Berlin that he desperately wanted. The opposition took a toll. Cantor suffered from severe bouts of depression, starting in the 1880s. He was hospitalized multiple times. He spent his later years partly devoted to trying to prove that Francis Bacon wrote Shakespeare's plays, an obsession that some historians interpret as a retreat from the mathematical battles that had worn him down. He died in 1918 in a sanatorium in Halle, malnourished during the privations of World War I. But his work survived, and it changed everything. David Hilbert, one of the greatest mathematicians of the early 20th century, called set theory the paradise that Cantor has created for us. And he meant it. Set theory became the foundation on which virtually all of modern mathematics is built. When mathematicians today define numbers, functions, spaces, structures, they define them as sets. Cantor's language is the language of mathematics itself, but Cantor's paradise had serpents in it. By the turn of the 20th century, Mathematicians were discovering paradoxes, logical contradictions that arose within set theory itself. The most famous was discovered by Bertrand Russell in 1901. Russell's paradox goes like this. Consider the set of all sets that do not contain themselves. Call it R. Now, does R contain itself? If it does, then by definition it shouldn't, because R is supposed to contain only sets that don't contain themselves. But if it doesn't contain itself, then it meets the criterion for membership in R, so it should contain itself. You're trapped in a logical loop. The set both contains itself and doesn't contain itself. Contradiction. This wasn't a minor technicality. It struck at the very foundations. If set theory was inconsistent, if it could generate contradictions, then anything built on top of it was suspect, and almost all of mathematics was built on top of it. Russell himself sent a letter describing the paradox to Gottlob Frege, a German logician who had just completed a massive 2-volume work attempting to derive all of arithmetic from pure logic and set theory. Frege reportedly replied that his work had been undermined at its very foundations. It's one of the most devastating academic letters ever written, and one of the saddest ever received. Years of careful work brought down by a paradox that could be stated in a single paragraph. This was a crisis, a genuine foundational crisis, and it consumed the mathematical world in the early 20th century. Russell himself, together with Alfred North Whitehead, spent the next decade writing Principia Mathematica, a monumental attempt to rebuild the foundations of mathematics from the ground up, using a more careful logical system that avoided the paradoxes. It took them over 300 pages to prove that 1 + 1 = 2. That gives you some sense of how deep the difficulties ran. David Hilbert, based in Göttingen, Germany, responded with characteristic ambition. He proposed a program, Hilbert's program, to place all of mathematics on a firm, consistent, complete foundation. The plan was to formalize everything, reduce all mathematical reasoning to manipulation of symbols according to explicit rules, and then prove, using only the most basic and uncontroversial methods, that this formal system was consistent, that it could never generate a contradiction. If you could do that, mathematics would be safe. The crisis would be over. The foundations would be secure. Hilbert was supremely confident. At a mathematics conference in Königsberg in 1930, he gave a famous address ending with the words, "Wir müssen wissen, wir werden wissen." We must know, we will know. He believed it was only a matter of time before the foundations were settled. He was wrong, and the man who proved him wrong was a quiet, eccentric, brilliant logician named Kurt Gödel. Gödel was born in 1906 in Brno, in what was then Austria-Hungary. As a child, his family called him Herr Warum, Mr. Why, because he asked so many questions. He studied in Vienna, fell in with the Vienna Circle of Philosophers, a group of logically minded thinkers who met regularly to discuss science, mathematics, and the meaning of meaning, and in 1931, at the age of 25, he published a paper that is widely considered one of the most important in the entire history of mathematics and logic. The title was dry, On Formally Undecidable Propositions of Principia Mathematica and Related Systems, but the content was explosive. The paper contained his 2 incompleteness theorems, and their implications are still reverberating today. Here's what Gödel proved. First, any consistent formal system that's powerful enough to express basic arithmetic will contain true statements that cannot be proved within the system. There will always be truths that the system can state but cannot demonstrate. The system is incomplete. Not because we haven't been clever enough, not because we need better axioms, but inherently, necessarily, unavoidably incomplete. Second, no such system can prove its own consistency. You can't use the system to demonstrate that the system is free of contradictions. If it could prove its own consistency, it would be inconsistent. These results demolished Hilbert's program. The dream of a complete, self-verifying foundation for mathematics was impossible. Not just difficult, provably impossible. Now, the proof is technically intricate, but the core idea is accessible, and it echoes something very old. It's related to the liar paradox. This statement is false. If it's true, then it's false. If it's false, then it's true. What Gödel did was construct a mathematical equivalent. He found a way, within any sufficiently powerful formal system, to create a statement that essentially says, this statement is not provable within this system. If the system is consistent, then this statement is true. It really isn't provable, but it's unprovable, which means the system is incomplete. There's a true statement it can't reach. It's a profoundly unsettling result. It means that mathematical truth is bigger than mathematical proof. There are things that are true in mathematics that we can never demonstrate, no matter how long we work, no matter how clever we are, no matter what axioms we choose. Mathematics has inherent limits, and those limits aren't practical. They're not about computing power or human intelligence. They're logical. They're built into the structure of formal reasoning itself. But here's the thing, and this is important. Gödel's theorems didn't stop mathematics. They didn't make mathematics useless or unreliable. Mathematicians kept proving theorems, kept solving problems, kept building structures of extraordinary beauty and power. What Gödel showed was that the formalist dream of total completeness was an illusion. But working mathematicians had never really operated that way anyway. They used intuition, creativity, analogy, guesswork. They explored and discovered, and sometimes got things wrong, and then corrected themselves. Gödel's theorems were a philosophical bombshell, but the practice of mathematics continued, vibrant and productive, because mathematics was never really about mechanical proof grinding. It was about understanding. And understanding, it turns out, is bigger than any formal system. And speaking of understanding and formal systems, the same set of ideas that led to Gödel's theorems also led, almost immediately, to one of the most consequential inventions in human history. Because the question Gödel was answering, are there limits to what formal systems can do, is intimately connected to another question, are there limits to what machines can compute? And the person who made that connection explicit, who defined the very concept of computation, and in doing so laid the foundation for the computer age, was a young English mathematician named Alan Turing, and his story connects back to mathematics in the deepest possible way. Because Turing's great 1936 paper, On Computable Numbers, with an application to the Entscheidungsproblem, was, at its heart, a paper about the limits of mathematics. It answered a question David Hilbert had posed back in 1928. Is there a mechanical procedure, an algorithm, that can determine whether any given mathematical statement is true or false? This was the famous Entscheidungsproblem, the decision problem. Hilbert believed the answer was yes. Turing proved the answer was no, and in doing so, he invented the concept of the universal computing machine. Independently, the American logician Alonzo Church reached the same conclusion at Princeton using a different approach, a formalism called the lambda calculus. But Turing's version, with its beautiful concrete image of a machine reading and writing symbols on a tape, was the one that caught the imagination of the world. Here's the beautiful thing about Turing's approach. To prove that there are limits to what algorithms can do, he first had to define precisely what an algorithm is. And his definition, the Turing machine, that imaginary device with its tape and its read-write head, turned out to be the theoretical blueprint for every computer that would ever be built. The very act of proving that mathematics has limits created the conceptual foundation for the most powerful mathematical tool humanity has ever devised. Limitation and invention, hand in hand. That's the kind of irony mathematics seems to specialize in, and computers changed mathematics itself in ways that would have astonished Euler and Gauss. Let me give you one example, because it's still debated and it raises fascinating questions about what mathematics even is. In 1976, Kenneth Appel and Wolfgang Haken at the University of Illinois proved the four-color theorem, the conjecture, dating back to 1852, that any map can be colored using at most four colors, such that no two adjacent regions share the same color. It sounds simple. It looks like it should be simple. And in fact, it's not hard to convince yourself that five colors always work. But proving that four suffice had resisted every attempt for over a century. Appel and Haken's proof was controversial, and here's why. It relied essentially on a computer checking a large number of cases. They reduced the problem to 1,936 configurations that needed to be verified, and the verification was done by computer, running for hundreds of hours. No human could check all the cases by hand, and this troubled many mathematicians. A proof is supposed to be a chain of reasoning that a human mind can follow, step by step, convincing itself of the truth at each stage. If the proof is a computer printout that nobody can read in a lifetime, is it really a proof? Do we really understand why the theorem is true, or do we just know that it is true? That distinction between understanding and verification is one that goes right back to the difference between Babylonian mathematics and Greek mathematics. The Babylonians had algorithms that worked. The Greeks wanted to know why they worked. When a computer proves a theorem, which kind of knowledge are we getting? The debate continues, but the trend is clear. Computers have become indispensable mathematical tools. They can explore vast landscapes of mathematical possibility, test conjectures against billions of examples, discover patterns that human eyes would never spot, and increasingly, they can also assist with proofs, not just checking cases, but helping construct logical arguments. Automated theorem provers and proof assistants, like Lean and Koch, are getting more powerful every year, and a growing number of mathematicians are formalizing their proofs in these systems, creating a kind of mathematical certainty that goes beyond what any human reviewer could provide. There's even a massive collaborative project called the Formal Abstracts Project, aiming to formalize large portions of existing mathematical knowledge, and artificial intelligence is entering mathematics in deeper ways. In 2021, researchers at DeepMind used machine learning to discover new patterns in knot theory, and to suggest a conjecture in representation theory that human mathematicians then proved. The AI didn't prove anything. It found patterns in data, patterns that pointed toward truths that human intuition hadn't detected. It's a new kind of mathematical collaboration, human and machine, and nobody knows quite where it's heading. Whether AI will eventually do mathematics independently, without human guidance, is an open question that touches on deep issues in the nature of intelligence and creativity, and the philosophy of mind. But the most emotionally satisfying mathematical story of the late 20th century isn't about computers. It's about a human being, working largely alone for 7 years on a problem that had been unsolved for 3.5 centuries. It's the story of how Andrew Wiles proved Fermat's last theorem. Remember Fermat, writing in the margin of his Diophantus, claiming he had a marvelous proof that the margin was too small to contain? That was 1637. For the next 356 years, mathematicians tried to prove it. They succeeded for specific cases, individual values of n. But the general case, Proving it for all n greater than 2 seemed impossibly hard. By the 20th century, it had become the most famous unsolved problem in mathematics. There was a common feeling that it might be true, but unprovable, or that the tools to prove it simply didn't exist. Andrew Wiles first encountered Fermat's last theorem as a 10-year-old boy, browsing in his local library in Cambridge, England. He was captivated by it, the simplicity of the statement, the centuries of failed attempts, the mystery of Fermat's lost proof. He told himself he would solve it someday. It was a childhood dream, the kind of dream most people grow out of. Wiles didn't. He became a professional mathematician, specializing in number theory, and in 1986, a stunning development rocked the mathematical world. Ken Ribet, at Berkeley, proved a connection that linked Fermat's last theorem to something called the Taniyama-Shimura conjecture, a deep statement about the relationship between two seemingly unrelated areas of mathematics, elliptic curves and modular forms. The connection meant that if you could prove the Taniyama-Shimura conjecture, Fermat's last theorem would follow as a corollary. And Wiles, reading about Ribet's result, realized that the childhood dream was suddenly within reach. The Taniyama-Shimura conjecture was incredibly hard, but it was the kind of hard that he knew how to attack. He had the tools, or at least, he had the beginnings of the tools. For the next 7 years, Wiles worked in secret. He told almost nobody what he was doing, not his colleagues, not even his wife until close to the end. He stopped attending conferences, stopped publishing papers on other topics. To avoid suspicion, he'd occasionally release a small paper on something unrelated, just to show he was still alive mathematically. His colleagues at Princeton assumed he was in a fallow period, that his best work was behind him. In reality, he was engaged in one of the most sustained and intense intellectual efforts of the 20th century, building an enormously complex proof, piece by piece, alone, in the attic study of his house, working every day for hours after his children went to bed. In June 1993, Wiles gave a series of 3 lectures at a conference in Cambridge. The audience grew as rumors spread about what he was about to announce. At the end of the 3rd lecture, he wrote the statement of Fermat's last theorem on the blackboard and said, "I think I'll stop here." The room erupted. Newspapers around the world carried the story. It was one of the rare moments when pure mathematics made front-page news. But the story wasn't over. When the proof was scrutinized in detail over the following months, a gap was found, a subtle but serious error in one step of the argument. Wiles was devastated. He worked to fix it for over a year, often in despair, sometimes on the verge of giving up. And then, in September 1994, while he was about to abandon the whole approach, the fix came to him. He later described the moment in terms that sound almost mystical, a sudden clarity, an insight that came from he knew not where, a connection between 2 ideas that he'd been staring at separately for months. The corrected proof was published in 1995, filling over 100 pages of the Annals of Mathematics. It was verified. It was correct. Fermat's last theorem was proved. 358 years after Fermat wrote his tantalizing marginal note, the problem was solved. Wiles received the Abel Prize, the Wolf Prize, a knighthood, and more honors than almost any mathematician of his generation. And the proof itself opened up vast new territories of mathematics. The techniques he developed are still being extended and applied to other problems today. It was a triumph, not just of individual brilliance, but of the accumulated mathematical tradition, Indian algebra, Galois theory, Cantor's set theory, the whole long arc of mathematical development over centuries, all coming together in one moment. And yet, for all that has been accomplished, mathematics remains full of unsolved problems. Deep, beautiful, frustrating problems that resist every attack. The Riemann hypothesis, proposed by Bernhard Riemann in 1859, concerns the distribution of prime numbers and is widely considered the most important unsolved problem in pure mathematics. It's been verified computationally for trillions of cases, but nobody has proved it. The Clay Mathematics Institute has offered a $1 million prize for a proof. It's one of the 7 Millennium Prize problems announced in 2000. So far, only one of those 7 has been solved: the Poincaré conjecture, a statement about the topology of three-dimensional spaces that had been open since 1904. It was proved by the reclusive Russian mathematician Grigory Perelman, who posted his proof in installments on the internet between 2002 and 2003 without submitting it to any journal. The mathematical community spent several years verifying it, and when they were satisfied, Perelman was awarded both the Fields Medal, the most prestigious prize in mathematics, and the Clay Millennium Prize of $1 million. He declined both. He declined the Fields Medal. He declined the $1 million. He withdrew from public life, reportedly living with his mother in a modest apartment in St. Petersburg. When a journalist tracked him down, he reportedly said, "I know how to control the universe. Why would I run to collect $1 million?" Whatever you make of that statement, it captures something about the mathematical temperament at its most extreme. The truth is the prize. Everything else is beside the point. And that sentiment, that the mathematics is what matters, runs through the entire story we've told tonight. From the anonymous Paleolithic person carving notches into a bone in Africa, to Babylonian scribes pressing wedges into clay, to Euclid carefully building his logical cathedral in Alexandria, to Archimedes drawing circles in the sand, to Al-Khwarizmi organizing algebra in Baghdad, to Fibonacci introducing new numerals to a resistant Europe, to Tartaglia and Cardano fighting over cubic equations, to Newton and Leibniz inventing the language of change, to Euler writing a third of an entire century's mathematics while going blind, to Gauss and Galois and Cantor and Gödel and Turing and Wiles. Through all of it, the common thread is this: human beings, confronted with patterns they can't quite understand, reaching for clarity, for structure, for truth. Mathematics isn't a collection of formulas to memorize. It's the story of people trying to understand the universe, armed with nothing but logic and imagination. And what they've found, what they keep finding, is that the universe has a deep mathematical structure that we're only beginning to uncover. The same patterns appear in wildly different contexts. The same equations govern the vibrations of a guitar string and the behavior of subatomic particles. The same geometric principles shape soap bubbles and black holes. The same prime numbers that fascinated the ancient Greeks now secure your bank transactions. It all connects, not always obviously, not always immediately. Sometimes the connections take centuries to reveal themselves, but they're there. And the thing is, we're not done, not even close. Mathematics is infinite. Gödel proved that much, at least. There will always be more to discover, more to prove, more to understand. Every answer opens new questions. Every theorem reveals new mysteries. The twin prime conjecture, the Goldbach conjecture, the nature of the Navier-Stokes equations, P versus NP, a question about the fundamental relationship between finding solutions and checking solutions that carries $1 million prize and could reshape our understanding of computation itself. These are problems that the best mathematicians alive are working on right now, problems that might be solved tomorrow or might resist every effort for another century. And somewhere right now, someone is lying awake in the dark, maybe a graduate student in Tokyo, maybe a teenager in Lagos, maybe a retired engineer in Sao Paulo, turning over a mathematical idea in their mind, pushing at the edges of what's known, reaching for something new. The same impulse that drove whoever carved those notches into the Lubombo bone 43,000 years ago. The same curiosity, the same stubbornness, the same quiet thrill of understanding. Mathematics is, at its core, a deeply human activity. It's the art of finding structure in abstraction, pattern in chaos, certainty in a world that offers so little of it. Mathematics was here before us. It'll be here long after us. The patterns don't need human minds to exist. The primes would still be prime. The circles would still be round. Euler's identity would still hold, even if nobody were around to write it down. But the fact that we can see these patterns, that we can prove they're true, that we can use them to build bridges and send signals to distant spacecraft, and understand the shape of space-time itself, that's the remarkable part. That's the human part. That's the part worth marveling at, quietly, as you let your eyes close and your breathing slow and the numbers fade into sleep. The square root of 2 is still irrational. Pi is still transcendent. Euler's formula still connects 5 of the deepest numbers in mathematics in one line. And you're made of atoms that follow mathematical laws, arranged in patterns that mathematics can describe, lying on a planet whose orbit is an ellipse, in a universe whose expansion obeys equations that Einstein wrote down a century ago. The math is everywhere. It's in you. It's always been in you. So let that settle. Let the names and the dates blur gently together. Thales and Euclid and Archimedes, Brahmagupta and Al-Khwarizmi, Fibonacci and Cardano and Fermat, Newton and Leibniz and Euler, Gauss and Galois and Cantor, Gödel and Turing and Wiles. They all pointed at the same thing. They all saw glimpses of the same enormous, beautiful, inexhaustible structure. And the fact that we can see it too, even a little, even dimly, is one of the quiet wonders of being human. Rest well. The mathematics will still be true in the morning.